Welcome to Data Science Decoded, where we unpack how analytics drives innovation and enterprise growth. In this presentation, we'll explore practical techniques, common workflows, and strategic considerations, so you can see how data science moves from experiments to measurable business value. Sit back and I'll guide you through the building blocks and real-world impacts, step by step. This slide shows how data science converts insights into measurable ROI, starting with core applications like personalized offers, demand forecasting, and predictive maintenance. The diagram highlights how those use cases can drive a 5 to 10% revenue lift and meaningful cost reductions, and why that justifies investments in talent, platforms, and governance to scale outcomes across the company. Here we present a cross-industry standard process, CRISP-DM, as a repeatable roadmap for projects. It starts with business understanding, moves through data exploration and careful preparation, then modeling, evaluation, and finally deployment, and the loop repeats. The visual underlines why alignment between stakeholders and iterative feedback is essential for practical, operational improvements. Data quality and cleaning are the silent hero of every project because messy, real-world data consumes most of the effort. The slide shows a structured cleaning pipeline, outlier detection and removal, imputation to fill gaps, encoding categorical fields, and normalization or scaling. Proper cleaning improves model accuracy more than fancy algorithms and is the foundation for trustworthy results. This slide explains supervised learning, where labeled historical data trains models to predict future outcomes. On the left is regression for continuous values, like forecasting revenue. On the right, classification assigns categories like spam detection or diagnosis. The flow from training sets through algorithms such as decision trees, SVMs, and neural nets to deployed predictions is illustrated across the bottom. Unsupervised learning uncovers hidden structure without labels, and this slide highlights three approaches: clustering for customer segmentation, association rules for market basket analysis, and dimensionality reduction to visualize high-dimensional data. The visuals show how grouping and pattern discovery generate hypotheses and actionable segments when you don't have predefined categories. In advanced forecasting, we compare ARIMA, profit, and LSTM models, and when to use each. ARIMA captures linear trends and seasonality for short-term forecasting. Profit handles multiple seasonalities and shocks, and LSTM learns complex, nonlinear, long-term dependencies. The takeaway is to combine model strengths to produce predictive insights and uncertainty intervals that support inventory buffers and risk hedging. Python is the de facto lingua franca for data science because it accelerates innovation from prototyping to production. The slide lists essential libraries: Pandas for data manipulation, Scikit-learn for classic ML, TensorFlow, and PyTorch for deep learning, and shows how open-source tooling, REST API integration, and cloud GPU scaling enable fast experimentation and enterprise deployment. The data processing ecosystem slide contrasts three pillars: Spark for in-memory distributed computation, enabling rapid analytics across clusters; Hadoop for cost-effective petabyte-scale storage on commodity hardware; and cloud warehouses like BigQuery for interactive SQL analytics with low latency. Together, they offer scalable options for storage, compute, and interactive querying depending on team needs. MLOps ensures accurate, auditable, and compliant model delivery by structuring pipelines into version and build, monitor and retrain, and deploy and consume stages. The diagram highlights version control, CI/CD, drift detection, scheduled retraining, and model serving through APIs, emphasizing lineage, reproducibility, and governance, so models remain reliable and traceable in production. This slide addresses algorithmic bias and practical mitigation strategies. Historical data can embed systemic inequities, so we apply techniques like equalized odds to balance error rates, counterfactual analysis to test causal scenarios, and transparent documentation to explain decisions. Those steps help detect skewed predictions, adjust thresholds, maintain stakeholder trust, and meet regulatory expectations. In closing, responsible innovation and democratization combine automated model search with ethical frameworks to deliver sustainable value. The visual links, AutoML, and simplified interfaces that broaden adoption with responsible AI practices, like fairness, explainability, and privacy by design. The goal is to scale insights across the organization while preventing harm, building trust, and ensuring long-term acceptance and compliance.